three things do you wish for the participants to take with them after this?
Thank you, Karen. It was a pleasure doing this. I think, to me, the most important three takeaways that I hope people got is, I guess, what 3D printing can bring to them in terms of adding value to what they do and how it can help them to innovate. Because to me, innovation is the way Sweden can move forward in terms of competing with the rest of the world. And I guess some of the versatility of what it can offer and how people are using it around the world. So those are probably the three takeaways I would hope they would get.
I'm so curious because this is a lot about innovation and doing prototypes, but when can we see really commercially gainable 3D printers? Is it the printers or the material or people that are the largest restrictions?
To me, it's about the people. To me, the printers are just tools.
Yeah.
So they're just tools that allow us to take ideas and make them real. So it's the ideas that are important, and once we have them, we use the tools, 3D printers, to make them real, and then sell them. And we're starting already to see it being used in real commercial business today.
And if you compare this to the music industry, where you have today iTunes and Spotify, could you see some similarities that some companies are chasing for the free software and people are trying to make money out of it?
We're already starting to see the whole open source movement moving into the whole 3D printing area. And much like you had iTunes and Spotify, we're starting to see similar systems like Thingiverse and GrabCAD appearing in the 3D printing world. But I think it's going to be one of those legal areas that in the near future, I think lawyers will make a lot of money trying to sort it out.
That sounds like great news. But what do you think about these breakfast seminars? Do you think they are important?
I think these breakfast seminars are incredibly important because this is how we as a university get the word out to the rest of the world of some of what we're doing. So it's a way of spreading the word of some of the research we're doing and how it can be used by companies, industries, and people in general.
Thank you so much.
Thank you.
So, good morning, everyone, and a warm welcome to this first event. This is the first seminar in a series of breakfast seminars held here at Ideon, who will bring out exciting research and for us to listen to and take part of and to discuss. My name is Karin Ebbinghaus. I'm currently working as a lawyer at the law firm Vinge in Malmö. And you might wonder, what is she doing here? And that's a question I quite often ask myself. What am I doing? But I think it's the reason behind asking a lawyer to be here is that if you have an idea and you go into a venture, you will need a lawyer to fix everything. And if your business is prosperous, you will need a lawyer to help you. And if your business is not prosperous, you will still need a lawyer to help you. So we are needed everywhere. And this first, you have here a folder on your chairs describing the different seminars for this autumn. And you have 4 occasions. And today, we have a very honorable guest, and it's going to be so exciting to listen to what Olaf Diegel is talking about 3D printing. And before I let you on the floor, I will just say that the setup of the seminar is that we will listen to Olaf for about 30 minutes, and then we will have a discussion for about another 30 minutes, and we will close this at 10 o'clock, so you can continue with your everyday Friday work. So the floor is yours, Olaf.
Thank you, Karin. Thank you. Oh. Good morning, everyone. My name is Olaf, and it's my job over the next, 30 minutes to tell you everything you needed to know about 3D printing. So that's going to be exciting. But I thought before I start, maybe just a few words about my background and where I come from. It's always good to start with the story of my life. So I was born in New Zealand, but I've lived just about everywhere. I grew up mostly in Canada, South Africa. I was in Japan for a while, and back in New Zealand for the last 23 years. Until a year and a half ago, I moved to Sweden, so I'm now officially Scandinavian. Yeah. And it's always good to show some embarrassing pictures of growing up. So we were the original Sound of Music family, just about. We were 5 kids in the family. My father's German, so I have horrible memories of having to wear leather shorts and strange outfits, and we had a little orchestra that played for our grandparents. The reason I mention that is later when I talk about the guitars, it'll all sort of start to make sense. My undergraduate degree, so when I studied in engineering in South Africa, I studied electronics, but I've never really worked in electronics. Today, I'm probably more of a mechanical engineer, and I do product development. But just to show you what a geek I was, what a nerd I was, while I was studying electronics in South Africa, I was also in a medieval music group where we played 13th century music. So, I mean, the ultimate geek, electronics and 13th century music. The cool thing here is Simon was doing his master's in medieval music, so we built all the instruments ourselves. And again, that comes back to my 3D printed guitars that we'll talk about earlier and later. Luckily, I didn't only play strange music, I also did a fair few stints in garage bands playing good rock and roll music, so that was a lot of fun. Much better memories, I think. What I do today is product development. So I develop products from concept through to manufacturing to getting them on the shelf out to the market. I did a lot of work. My previous job was as professor of mechatronics, which is the technical side of product development, mechanical, electronics, and software combined. But overall, throughout my career, it's always been developing products for the last 30 years or so. I've done a lot of home health monitoring products, lighting products, medical products, marine products, all sorts. And this is what got me interested in finding better ways of developing products faster, getting the right product to the market as quickly as possible. And that first got me interested in computer-aided design as a tool to get stuff out of our brains onto something that is manufacturable. And then in the mid-90s, I discovered 3D printing. And that was amazing. That really changed how you did stuff, because suddenly you had a technology that allowed you to take what you had imagined and make it real. And that's what we're going to be talking about today, sort of 3D printing, what it's being used for today and what it is. So, the old-fashioned way of making almost anything. If I wanted to make a bust of my head, I would start with a block of material, a hammer and a chisel, and I'd cut away all the material until you're left with a head. So subtractive manufacturing, where you're removing material. And this is still the way that 99% of things are made today, but with not a hammer and chisel, but a CNC machine, which is a computer-controlled cutter that cuts away all the material. And even if you're injection molding plastic parts, you still make the mold through subtractive means. Additive manufacturing is completely different. You start with nothing. You start with a virtual computer model, and the machine slices it up into very, very thin slices, and then this is where the term 3D printing comes on. It prints one slice on top of the next, and then layer by layer by layer by layer, it builds up your 3D part. And of course, the thinner those layers, the more perfect the part becomes. If you have thick layers, you get almost a staircase on the side. As they get thinner, they get better and better and better. So later, there'll be some videos that explain the layer upon layer printing perfectly. But to me, what makes 3D printing really exciting is it's been around for close to 30 years. Probably 1989, the first commercial machines started appearing. And since then, any company that's involved in product development has been using it for prototyping. You have an idea for a product, and before you spend big money on tooling up to make it, you do a quick prototype just to make sure your idea is perfect. And still today, this is probably the way that the majority of 3D printers are being used, for prototyping. But what's really exciting is over the last 5 or so years, the technologies have started getting good enough that you can now start to make the real product to sell to the customer. In some cases, if it's high value enough. So the next sort of 20 or so slides are some of the advantages that 3D printing has over conventional manufacturing. Now, don't misunderstand me. 3D printing will never replace conventional manufacturing completely. There will always be a role, in mass manufactured high value volume products will always be made with conventional methods. But 3D printing has some advantages that, if you use them, can give you tremendous advantage over conventional manufacturing. And the first and best known one of these is complexity for free. Now, what we mean by complexity for free is that the more complex the object is, the better suited to 3D printing it is. So with conventional manufacturing, as your part gets more and more complex, it becomes more and more expensive to make, to a point where it becomes impossible to make. And have a look at this as an example. This is sort of an artwork, but this is an incredibly complicated shape that would be completely impossible to make any other way. But with 3D printing, it's perfectly suited to it because it is so complex. So this is one of the things that makes 3D printing exciting. If you can imagine something and you can get it into a 3D model, typically there's no limits to being able to manufacture it. And that really changes the way you do things. So some examples of this in the world of art and design. Artists absolutely love this technology because artists have been very sort of proactive in learning digital tools for getting their ideas into computers. Now they can hit the print button, and a few hours later they've got these amazing things that would be pretty much impossible to make any other way. So it really has, I mean, the artists are really pushing the limits of what you can do with these machines. And in our lab in New Zealand, it was actually the artists that were pushing us as engineers the furthest, because they'd come in and ask us some incredibly, we thought stupid questions saying, can you make this? And we said, oh, what do we do now? And we tried to figure out a way of doing it, and we were surprised that often you could do it. Stuff that you couldn't make any other way. So it really does change the way you do a lot of things. So again, most of these objects would be pretty much impossible to make any other way. Here's a nice other example of complexity for free, a Klein bottle. It's one of those mathematical models that is impossible to make. It's all one surface, so the inside of the bottle becomes the outside of the bottle. And it's a really nice example of impossible shapes to manufacture any other way. This is a fairly recent example. This is an American company called American Standard, and they've started making a whole range of deluxe tapware. Again, look at something like this. How does the water get up there and come out of the tap? You know, it's these impossible shapes that you couldn't make any other way. It's because with 3D printing, you can make all these curved pipes that you couldn't make any other way. Incredibly beautiful objects. I mean, these are absolutely fantastic. I would love a set of these for my kitchen. The catch is a full set of them will cost you 12,000 US dollars. So there is still a catch there. It's high value items. But again, this really shows off that complexity for free really nicely. The more complex something is, the better suited to additive manufacturing. So just to go back a step, the technical term for what we're talking about is additive manufacturing, but most of the media calls it 3D printing. I use the two interchangeably. They mean exactly the same thing. This is a really nice example from the world of marketing. So this is an example by Onitsuka, which is the Japanese company that makes Asics running shoes. And it was called the Electric Tigerland campaign, and they made a Japanese city in a shoe. And they did a big sort of 70-centimeter model and a few smaller ones, designed by a Dutch artist called Janne Kietanen. Really incredible, and look at the complexity. I'll just show you some close-ups. Look at the close-ups of this, and again, try to imagine making this by hand. You would be here for the next 3 years with little carving tools trying to make it. It would just be impossible. With 3D printing, loves it. The more complex, the better. And this is also a very nice example about thinking differently, which is one of the things I like about 3D printing. So this was done purely as a marketing campaign. And on YouTube, they've got videos with the camera flying around the shoe, and it's all beautifully lit up, and you can see close-ups. And the campaign went viral, and it got very, very popular on the internet. And people said, that's incredible, can we buy some of these? So Janne started making a range of silver keychains and little memory sticks based on the marketing campaign. And it kept growing and growing and getting more and more popular until Onitsuka started actually making a range of shoes based on the marketing campaign. And this is what to me is quite interesting. It's the only example I know of where the marketing campaign has generated the product rather than the other way around. And 3D printing does that. It makes you think differently. And because of that, you see a whole range of new innovations that you wouldn't have had any other way. So these are, shall we say, the aesthetic advantages of complexity for free. One of the more interesting ones from an engineering point of view is the possibility to lightweight products, to make products that were traditionally heavy, very, very light. So this, the accessory that everybody should have, this is my little titanium 3D printed bottle opener. So it's a little titanium 3D printed bottle opener, and you can see it's made out of a very lightweight truss type structure. That means you can remove up to 90% of the weight of a product, yet still maintain the same mechanical characteristics. So this is rated at 300 kilos to break. Aeronautic industry, for airplanes, this is huge. So the airplane industry is probably the one that is adopting this the most. Every gram you can remove from an airplane part saves you tens of thousands of dollars a year in fuel costs. There is now software that'll automatically do this for you. It's still new, it's not perfect yet, but software like Solid Thinking and Inspire, where you put in your CAD model and it'll remove most of the material. But just to give you some numbers on that, if you were going to make this bottle opener the traditional way, you would start with a block of, if this was aluminium, the block of aluminium would weigh about 10 grams. You would then put it on your CNC machine, and you would machine away as much material as possible, and it would weigh maybe about 4 grams. You might be able to machine a little bit more from the inside, maybe get it down to 3 grams or so. Compare that to the optimized one, less than a gram. That's a 90% saving. Now, this is an extreme example. Typically, they can easily get 30 to 60% weight savings on most engineering components. 90% weight saving is pretty extreme, and it's for something not very vital. So complexity for free in this scenario is getting used more and more for engineering purposes, both aeronautical, automotive, any products that benefit from being lighter and stronger. Next big advantage, if it moves forward, is mass customization. So what we're talking about here with conventional manufacturing, every product has to be the same. And that's because you put a lot of money into a tool to make the product. So to make a different version for a new customer costs a lot of money. With 3D printing, every product can be different without it costing you any more. So this is what we talk about mass customization, where we're going to mass manufacture, say, for example, shoes for this entire audience, and every pair of shoes is custom made for you, but without it costing you any more than it would with conventional manufacturing. So this is something that over the next few years we're going to see more and more of in terms of real manufactured product. And probably the most used today is in the medical field. And that's because our bodies are all different, so it makes sense that when we need something that fits our body, it's custom made to fit us perfectly. Today, over 96% of inner ear hearing aids are 3D printed. We don't even know they're 3D printed. We don't care how they're made. We just care that they fit us perfectly. So they'll put some silicon in your ear, pull it out, and they'll scan the silicon plug of your ear. They've got software that'll automatically shell it out, put in the screw mounts for the electronics, and then overnight they'll print 1,000 hearing aids, each one custom made for an individual user. Hip replacements, dental aligners, crowns, a lot of implants are being custom made today. And again, this is fairly interesting. The hip replacement on the inside is like a ball joint, so that's actually machine smooth. The printing quality today is not good enough to make a nice smooth ball joint, so they have to machine that afterwards. But the outer surface, you can see, is porous. It's like a mesh structure, and the reason for that is when you implant it, the bone grows into the titanium, so you get a full strength, lightweight replacement. And that means if your grandmother has a hip replacement, she's not going to need to go into hospital in a few years to get it tightened up. As I understand it, with conventional hip replacements, they get loose and they have to be tightened up every few years. With this, because you get bone growing into it, it sort of solves that problem. This assumes you have bone growth, of course. But yeah, so medical area is one of the big areas of mass customization, and we're only just starting to see this happen today, but over the next 5 years, it's going to boom. This is an example from New Zealand. So Massey University, my previous university, the vet school there had a dog with cancer of the jaw. So we printed out a titanium jaw replacement for the dog, custom made for that dog. They implanted it, and the feel-good part of the story is that within 24 hours, the dog was eating again. And that's quite impressive. That's very impressive. And again, you can see very lightweight structure where they've removed a lot of the material, keeping it strong but very lightweight. So again, that advantage of complexity for free. So this whole area over the next 5 years, I guarantee you, is going to grow. And we're going to start to expect custom-made product. And already there's 4 companies that are doing shoe inserts where very easily they can scan the bottom of your foot. Even from an iPhone picture of the bottom of your foot, they can generate a 3D model, print you out a pair of shoe inserts that'll make your shoes fit you perfectly. And there's 4 companies doing that already. So I think we as customers will be changing. It'll become an expectation for us to expect products made for us. This is a nice example, A, because of my interest in lighting. I've done a lot of work in the lighting industry. So all of these shapes, again, complexity for free, incredibly complex shapes. These are all printed in one piece. They're not lots of separate pieces assembled together. But this one in the middle is a nice example. It's a British artist called Lionel Dean, and he loves genetic algorithms. So he's written some algorithms, and on his website, that light is continuously morphing around, twisting, changing shape, adding and removing tubers. When you see a shape you like, you say, stop, buy now, and then 2 weeks later, you get a light that nobody else in the world has got that same light. And that is quite cool. It's not going to save the world, but from a custom product point of view, it is a very, very nice example of being able to use that mass customization to big advantage. I think now on his website, he's actually got a different one. It's no longer the tuber. It's now one with lenses, and it keeps adding, removing bigger and smaller lenses. But the same thing applies. You can stop at any stage and buy the light. And of course, the ultimate in 3D in mass customization would be 3D printing people. So this is quite old. This is probably about 10 years ago, which was wedding cake toppers, where you can make little mini-me's for your wedding cake. This was huge in Japan, where weddings are a big thing in Japan. So being able to 3D scan yourself and have mini-me's on top of your wedding cake is big. Star Wars now licensed the figurines, so you can buy a stormtrooper with your own head on it. This was me in Berlin last year. I think I had myself fully body scanned in 7 seconds to do a full body scan and print you out in color. The printing doesn't happen while you wait. It's still a fairly slow process. So a week later, I got a little FedEx box with a 3D printed mini-me in the box. A lot of fun. And there's now photo booths, so it's now becoming a growing area of business where people, instead of having 2D photo studios, now have 3D photo studios where they can scan you. And a lot of the gaming technology, the Kinect gaming sensors, are now being used to very easily do 3D scans in full color that you can then print from. You can go to Disneyland with your kids, scan their face, and print out a Cinderella doll with your child's own face on it. Now, quite an interesting application. And you start to wonder a little bit about sustainability, that if you make a toy for your child with their own face on it, will they keep it longer than one with just a generic face on it? We don't know the answer to that, but I suspect they might keep it a bit longer, which makes the toys maybe a little bit more sustainable. Now we get to the slightly more complex area, the ability to print complete products. So two things we mean by that. A is for example, we have an example here. This is called a brain gear, and it's a little ball made up of gears that all move. The whole thing is printed in one piece. So it comes out of the machine, assembled, ready to go. And that is pretty impressive. And we've got another little example here, which is it's a little radial airplane engine model with a handle on the back. All the pistons move. But again, no assembly required. Comes out of the machine already assembled. So you can now start to reimagine your products that used to be made of many moving parts and make them all in one piece. There are limits because the precision of these machines is still relatively low. So there's limits to what you can do with it. The other thing we mean by that is you can take a product that was made up of many simple parts, and now you can make it out of very, very few, much more complex parts. So because you can now print in plastics and a whole bunch of different metals, you can start to do what's called part consolidation, where you take a product that was made of 10 or 15 or 20 different parts, and now you can make it out of 1 or 2 parts. And the first example of that is an example from NASA, where they take essentially a rocket engine, and they've gone from what used to be 115 separate components, they can now make in 2 components. And that's the 2 components there, the front and the back. Everything else, all those complex channels that used to carry fuel, all printed as a single incredibly complex part. So that's a really nice example of part consolidation, going from many, many parts to much fewer parts. To give you another example, this is an example that I was involved with in New Zealand. This was for the New Zealand Navy. The New Zealand Navy are the ones that operate all our drones in New Zealand, so our UAVs, the unmanned aerial vehicles. And this is what's called a pitot tube. It's a little tube about that size that sits at the bottom of the airplanes, and it measures airspeed. It's inside, it's got lots of different compartments, and you look at the pressure difference between compartments to measure airspeed. The way they've been manufacturing them until now was out of 32 different components brazed together. The first redesign we did for them, we printed as a single plastic component, and it worked. What we didn't know at the time, and as we gave this to them, they tested it out, but what we didn't know is when these airplanes land, they often land on the beach in the sand, and the pitot tube, which happens to be at the bottom of the airplane, would dig into the sand and would get filled up with sand, and it was always a problem to empty out to clean out. So the final design, which is now in production, has a separate front tube with a little rubber O-ring that you just clip on, and that's to make it easier to, after landing, you can just clip it off, empty the sand out, and be ready to fly again. This is now 3D printed in titanium, and they use these in production on their UAVs. But think about it, going down from 32 separate components and a lot of labor, because somebody has to stand and braze all these components together, into 2 components and more or less no labor. So I exaggerate a little bit because there is labor involved in 3D printing in metal, but compared to brazing them together, it's an incredible reduction in complexity and in time and so on. Now we get to the fun part. So this is, so far, complexity for free, mass customization, and part consolidation are what I would think of as engineering advantages. Now we get to the softer side of things, which is the ability to try out ideas at no risk. If one of you has an idea for a product you want to take to market, typically it's going to cost you 100,000, 500,000 crowns, 1,000,000 crowns, just to realize your idea and get it to market. That's a lot of investment, that's a lot of risk to take. 3D printing removes that risk. You can now take your product to market at pretty minimal investment. And the first example is actually one of my students in New Zealand called Jenna, who is a mountain biker. So she runs around the world with Red Bull doing crazy things on mountain bikes. And when she travels, she's got a big cardboard box with a bicycle in it, and it's hard for her to transport around the airport. So as a third-year design project, she said, I know, I have an idea. I'll make a little set of wheels that I can clip onto any cardboard box just to make it easier to transport. It's a simple idea. I think it's quite a clever idea in a way. The entire bracket and the clip-on thing is 3D printed. The wheel is from a skateboard wheel. She made these, and she's been using them since then to travel around the world, and it makes her life a lot easier. Now, the other athletes who see her say, ooh, that's cool. Can we buy some of these? So she says, all right, what do I do now? Okay, I'll sell you a pair. And she sells one pair and another pair. And I lost touch with her about 2 or 3 years ago, but 2 or 3 years ago, she'd sold about 70 pairs of these. So I wouldn't call it a business yet. I wouldn't even call it a micro business yet. But she has been able to test her idea for the market. And from here, she can decide, yes, there is a market for this. It's a low value product. I will now spend some money on injection molding it. Or it's a high value product. I will now keep manufacturing them this way. But the point is, she didn't have to invest a lot of money to get to this point. And that brings us to my own example of the 3D printed guitars. So this was in 2011. The Economist did a story called Print Me a Stradivarius, where they took the CAD files off a Stradivarius violin, or the blueprints, CAD'd them up, 3D printed it. So these are the 3D printed violins coming out of the powder. I saw this story and I said, that is amazing. And from my younger days playing in rock bands, and because I've been using the technology for about 20 years now and seeing it getting better and better and better, I thought, I wonder if it's possible to make an electric guitar. So I was at my parents' place in South Africa on holiday. I was bored, so I designed my first one, got back to New Zealand, printed it, and I was amazed by how well it worked. I was actually blown away because I was expecting it to be pretty so-so, but it worked incredibly well. So I started a blog about it, saying, look, here's something really cool. Isn't this amazing? And musicians from around the world started to respond, saying, that's incredible. Can we buy one? So I said, ooh. What do I do now? Scratched my head a bit and said, okay, I'll sell you one. And I sold another one. And today I've sold 52 of them. So again, it's a nice hobby side business. So just to show you the violin, to show you that it is a working violin. And in this case, the entire violin, except for the arch and the bridge, are printed in one piece. Oh, and the tuning pegs. But the neck, everything else printed in one piece. And yeah, well, and the strings as well, I suppose, yeah. But it sounds like a violin. Now, the professionals who play it say it sounds like a violin. It's a bit heavier than a violin. But you've got to remember, this was not done to create the ultimate violin. This was done to show it could be done. And possibly you could make the ultimate violin, but you would need to redesign for the different material. And the advantage this has over wood is it's consistent. So once you get the ultimate violin, you'll always get the same violin. Whereas in wood, it's always going to be a different violin. So with my guitars, I do about 12 different designs now. Here's some of them, just to show you the range. Now, all of these show complexity for free. These are all complex shapes you could not make any other way. Inside the guitar here, we've got all of New York City. Inside the guitar is Brooklyn Bridge, all the sites of New York inside of a guitar. This one here down the bottom is a steampunk. I brought it in today, so for those of you who want to have a look afterwards. And the nice thing about it is you've got all the gears moving. But again, all printed as a single piece, the body. So it's just the body that is 3D printed. The neck is a conventionally made CNC neck. We've got a cast bridge, injection molded plastic pickups, and so on. But it really shows that area of complexity for free, and moving parts, and mass customization, because every guitar I make, I custom make for the musician. So it really shows you some of the advantages of 3D printing. And because I made a guitar, it sort of made sense that I should also make the rest of the band. So eventually I made a drum kit, a keyboard, and a saxophone. The saxophone doesn't really work yet. It's sort of my first generation. The next generation should work a lot better. And then we'll have a full 3D printed band, which will be a little bit more fun. Now we get to the really soft stuff, which is not about making money, but just about being creative and trying out new ideas. And to me, this is one of the nicest things about 3D printing. It removes that barrier of manufacturing, which often stops us realizing our ideas. And the first example is actually one I did fairly recently. I did it over the summer holidays. This is my iPad. It's an iPad 3. As it happens, the iPad has a speaker on the back, which is a really dumb design decision from Apple, who you think would do better than that. That means the sound goes out the back of the iPad. So A, the sound quality is not good because the bass is pretty omnidirectional, but the treble all goes straight out of the back. So you don't get a particularly good sound quality. But worse, when I'm lying in bed watching my iPad, it's pointing towards my wife and she's getting irritated because she gets all the sound I don't. So very quick experimentation. You just put your hand over the speaker and suddenly the sound becomes crystal clear and crisp because you're redirecting all the treble towards the front. And first I put a little post-it note on the back, fold it over, and that worked, but it was a bit clumsy. So I said, no, I'll just print myself out a little clip-on bit that you clip onto your iPad and now redirects the sound to the front. And it works amazingly well. So now I cannot listen to my iPad without this because it's just such an improvement in sound quality. The point is you have an idea and you can instantly try it out to see if it's a good idea or a completely stupid idea. And that, to me, is one of the real powers of 3D printing, is being able to try out ideas very quickly. You've now got desktop printers that'll cost between 5,000 and 20,000 crowns. You can buy them at MediaMarkt. They're not the same as the industrial printers, but they allow you to test your ideas, and that really is pretty amazing in terms of being able to, try out your ideas as quickly as possible. Another example, this is a weird one from about 6 or 7 years ago, an artist called Marcus Kaiser. And he goes out into the Sahara Desert and he makes glass sculptures by 3D printing in sand. So he spreads a layer of sand onto his platform, and then he's got a lens that he moves around using very, very open source electronics. So he just moves it around like a magnifying glass. When you focus, when we were kids, we used to do that to ants, which is probably not a story I should be telling, but you burn wood and you trace it around. So he does the same thing. He just moves the lens around and melts the sand and makes these incredible glass sculptures. From a creativity point of view, that is incredible. And there's some good videos on YouTube. He spends about a week in the Sahara living in one of those silver tents while he's making these glass sculptures. Pretty amazing. So if you just Google, go to YouTube and look at Solar Center, you'll come up with some very nice videos on that. And then we get to the most interesting area. So this is a project called Enabling the Future. Low-cost prosthetic hands for developing countries. So it was started by a South African called Richard Van As, who lost 2 fingers in a carpentry accident. So he teamed up with an American and they did something called the RoboHand, which was a low-cost desktop 3D printer-made prosthetic hand that cost about $100 to make. Really incredible. So they then started a movement called RoboHand, making a low-cost prosthetics for developing country, which now has blown into an open source organization. So you can go to Enabling the Future, download plans for prosthetics, customize them to fit your purpose, and then print them out for between $50 and $150. Then you re-upload your designs for other people to download in case they've got a similar condition to yours. So what I like here is, you're solving a good social problem. These are countries where they cannot afford the expensive first world country prosthetic hands. But what I like most about this is the concept of open source innovation. And you think about companies all individually trying to solve technical problems they have, why not give them to the world and get the whole world to try help you solving your problems? And this is one of the things 3D printing does, because now a lot of people have these desktop 3D printers at home. You can now get the entire world to try help you solve your problem. So this is something that companies are starting to know about, and hopefully will start to do some of this over the next few years, is get the rest of the world to help you. So really, really nice area. So I think we have enough time, just enough time to go into the supply chain, how the supply chain will change over the next few years. And what we're talking about here is on-demand manufacturing, making parts where you need them, when you need them. And that is, again, a great area of change. So instead of having warehouses full of spare parts, we make them as and where we need them. NASA doing a lot of work in this area. So instead of having to send rockets up with spare parts to the space station, they print them on the space station. And in fact, they've got a 3D printer on the space station now. A lot of companies in Sweden are starting to look at this area to see what they can do by way of replacing their spare parts business models. And I thought just a few more to finish off is some of where it's heading in the very, very near future. So some of the areas of future development. And the first one is probably one that's fairly well known about, is the idea of 3D printing houses. And this is a little animation showing how 3D printed houses would work. So this is done by the University of Southern California, and it's actually incredibly simple. It's essentially, this is a pipe system and it's extruding concrete. It's like toothpaste tube, and you're squeezing toothpaste out of a toothpaste tube, and it's just squeezing concrete out layer by layer. So in this case, it's starting to print the walls. And for those of you who don't understand that layer upon layer upon layer principle yet, this shows it beautifully. So it's about to finish the first layer, and second layer now starts, and it's going to keep going layer by layer by layer, adding concrete to the house. Very, very simple in terms of how it works. What it's doing is incredibly complex, but the technology is pretty simple. With this particular concept, you have a problem that when you get to the top of the windows and the top of the doors, you can't print in air. It's just going to collapse. So with this technology, normally you have something called support material, which is sacrificial material you break away afterwards. Here they've come up with a different solution. You'll see on the right side, there's this green robot waiting over here, and it goes and picks up beams, lintels, places them above the doors and the windows, so it can keep printing for the next layer, and then it keeps printing. Just to show you where, so this is a science fiction video to show you where they're at in reality today. This is the same machine in the lab at the University of Southern California built by students, and this is doing exactly what you saw in the previous video clip, but printing in clay. So it's just squeezing clay out of a nozzle very slowly, and it's doing a 3-leaf clover shape, and it's going to, when it gets back to this point, you'll see it jump up. Here we go, and layer 2. And just layer by layer by layer, it builds it up. In this case, it's only smoothing the outside layer because the inside is where the electrics and the plumbing will be, and so on. And it's not just limited to straight walls. You can curve walls and do arches just by stepping in a little bit each time. So in a few seconds, we're going to see it jump to the bigger machine in the lab. So this is exactly what you saw in the video animation, but now in real life, printing in real concrete. Very simple. It's just squeezing out concrete. In this case, it's concrete with special chemicals in it that stop it from slumping, from sagging when you print it. So Prof. Koshnevis, the guy from the University of Southern California, he's been working on this for at least 18 years now, I think. And his estimate was by the time the technology is fully mature, 48 hours to print an entire house ready to move into. Probably about 8 months ago now, the Chinese said that's not good enough, and they printed 10 houses in 24 hours. So whether that number is accurate or not, we don't really know, but it's still pretty incredible. And also they did it differently. They printed sections of houses, as you see there, in a warehouse, trucked them to site, and essentially glued them together on site. So here you can see the sections making up the site that were glued with concrete together on site afterwards. But still pretty amazing. They've now done an entire hotel villa in the Philippines, an apartment building in China. So it's still early days, but it is happening. And now in Sweden, there's quite a few efforts. So Umeå University is working on printing a house in cellulose. A lot of the other companies are working on printing with concrete. So a growing area of research. So this is large scale, big 3D printing to show you the opposite end of the spectrum. On the small side, nano printing. So this is science fiction. These are inside your bloodstream. We're going to have these little nanobots flying around and keeping us healthy. They're going to be eating the cancerous cells or what have you and keeping us clean. So we're not at this stage yet, but to show you where we are in terms of small size, the nano bull. So this is a Spanish fighting bull printed in 3D using a technology called femtosecond laser manufacturing, 1/10 of a human hair in size. So we're not at the stage of these little robots yet, but we are getting pretty small. You know, the fact that you need a microscope to see it is pretty amazing. This one's a little bit harder to see. We have a square frame just off the picture, a spring, and a suction cup. And when you shine a laser on it, the suction cup releases, the spring shortens, and the frame moves along. So this moves along like an inchworm. It's like one of those worms that stretches and walks along. Very, very simple micro machine. Again, nowhere near this stage yet, but it's baby steps in that direction. So who knows, 5 years, 10 years, 20 years, will we get to that level where we can print nano machines? Probably yes. You know, it's not that far away. And probably one of the fastest growing areas of research is bioprinting. So printing body parts. So using your own stem cells to print, in this case, they're printing from an inkjet printer with stem cells, and they're printing the heart of a mouse. Layer by layer, laying down cells with the heart of a mouse. So this is probably one of the fastest growing areas of research in the world. As I understand it, your own stem cells are pre-programmed to make the tissue they're programmed for. If you print them in the right configuration, they will become a bladder or a heart or what have you. Today, there's one commercial company called Tengion out of the same university, out of Wake Forest University, doing human bladders that are 3D printed. There have been quite a few sort of tracheas, heart valves that have been 3D printed over the last few years, but we're still a reasonable time away from being able to do more complex organs. So what they cannot do today is kidneys, hearts, livers, and so on. And that's because of the vascular system. They cannot print out the small vessels that carry the blood around yet. Once they are able to do that, I think very, very quickly they will be able to print full more complex organs. And again, think about the implications this is going to have on our lives. Very, very interesting implications on our lifestyle, on how long we live, ethical implications that we haven't even started to think about. So as I said, this is the fastest growing area of research in this area around the world. And I think Chalmers about a year ago did an ear. They 3D printed an ear, so it's happening in Sweden as well. And the final one I'll leave you with is food printers, which again is a booming area around the world. And you can now buy certain types of 3D food printers. So this is the concept from MIT Media Lab, and on the printer you've got all of these cans at the top, which are the raw ingredients, flavoring, color, vitamins, soya, whatever the base ingredient is. And the concept is you walk up to it and say, I'd like a cheeseburger, medium rare, and then from those ingredients from the bottom up, it'll build it up layer by layer by layer to make you the food you want. So this is not happening yet today. So printing food, no, actually, the only food that is being printed today that I've seen so far is 3D printed meat. And it's using exactly the same technology as the bioprinting for organs to print meat from bovine stem cells and essentially growing it into meat. And I think they did a chef program where they had a 3D printed hamburger that cost something like $30,000 or something like that, because it was still science. But what a lot of people are doing is printing with food. And for example, printing with pasta. So anything you can put in a syringe, you can print pasta, you can print ravioli, print pizzas. Printing in sugar, where you can print full color sugar cake toppers. Chocolate is now very common. You can now buy commercially available chocolate printers. This was actually a nice promotion from the Fab Cafe in Shibuya in Japan, where they did the sort of a Valentine's Day promotion. We'd buy a box of chocolates for your boyfriend or your girlfriend, and there was a mini-me head sticking out of it. So I'm not sure how good an idea it was, but still, it's quite cool from a creative point of view. And she is a little bit frightening, I think, in this case. But the idea was very nice. And we're in the process of building one of these at EcoDC. So hopefully by the end of the year, we'll have a little chocolate printer up there for when we have, Kulturnatten or things like this, we can print little chocolate flowers. So that'll be a little fun. So hopefully this morning I've given you guys a quick overview on a little bit of what 3D printing is being used for around the world and some of where it's heading in the very, very near future. And it's frightening how close some of the stuff is to happening. So I think I'll leave it with there, and we'll sort of open it up to questions. And if there's got any thoughts, discussions, questions, and so on, over to you guys, I guess.
Firstly, thank you for a great presentation. Today is mind-blowing. I read about clothing.
Yes.
Clothing. There was no mention about.
Yeah, it's part of the art. So there are entire fashion shows dedicated to 3D printed textiles and clothing of various flavors. Yeah, and again, typically there are plastics, they're polymers. So this is nylon in this case. There are other types of plastics. Most of it, almost all of it has been in this form. Early days, it was rigid stuff, and you'd see the fashions walking on the catwalk, models that are walking like robots because they couldn't move. Now they're doing much more flexible textiles, which is much better. And I have seen one example where they're using electrospinning to make textiles in 3D. So they spin a shape around and electrospin over it as a new way of making 3D printed models. So yeah, it's a growing area as well. No, there are full color printers available now today. The problem is they're so expensive to run that you almost can't afford to use them other than for small parts. But there are full color plastic printers that will do that today. And as the prices get cheaper, we're going to see more and more of that coming out. Not in textile yet. It is a growing area of research, though. Yeah.
Could you mention the status of the design software?
Yep. It's actually a really good question. So to me, in a way, software is one of the areas that is behind the rest of the world for this. I mean, CAD software in general is still very, very hard to use. It's easier than it was 15 years ago. 15 years ago, you had to be a bit of a rocket scientist to run CAD software. Now, engineering software like SolidWorks, Creo, Inventor is becoming easier to use. But to me, where we could learn a lot is from the gaming software. Because gaming software is, in fact, advanced CAD software. But kids are doing this, and they don't even know they're doing CAD, yet they're doing these incredibly complex models of building CAD. And I just thought, we've got enough time to very quickly show you an example. This is a game called Spore Creature Creator, which is a free download. You can download off the internet. Your kids can play with it. This is the English version of the program. My Japanese nephew, who's 5 years, not 5 years old anymore, but when he came to play with this, he was 5 years old, and he was building some incredibly complex 3D printed models. It's not coming out on here, so we'll have to skip it. It's showing on my screen beautifully, but not over here. But it's a game where you design dinosaurs, and you pull and you stretch, and you've got libraries of heads and eyes, and you drag them and drop them, and incredibly easy to use. And I'll just show you what it looks like. So we're going to design a creature, and we'll start with this, where we start with a different shaped one. Let's go with that one. We can rotate around. We can say, okay, I like this one, but I want to give it a longer tail, for example. Maybe stretch its neck out a little bit. Let's give him a longer neck. Give him a head over here. That'll do it. We'll give him some eyes. Maybe give him some of these eyes over here. Maybe instead of ears on the back, maybe there. Some legs and feet. So give him a few arms there, wherever we want. Give him some feet. And his arms are too short, so I want to make his arms a bit longer. We can rotate him around. We can now give him a paint job to make him look like, say, something like that. We like that. We can now give him a test drive in a real environment, and we can say, make him do the spin. We can now give him a few children so they react the same way. 1 child, 2 child, 3 child. Make them all come this way. Make them face up. Make them do, let's all make them spin. Mummy does a spin, all the children try to do it as well, and so on. The point is, this is advanced CAD. There's really complex inverse kinematics behind that, doing all of this. Yet a 5-year-old in a few seconds can do this incredibly complex CAD. Why isn't design software working in exactly the same way as this? So let's say I'm designing a cell phone. The battery is fixed, I cannot touch that. The keypad has to have certain ergonomic constraints so it's reachable. But the rest of it, why is the customer not able to do things like this to design their own cell phone that can then be printed and made and still have all the engineering constraints hidden behind it? So to my mind, to answer the question, the engineering software needs to learn a lot from gaming. I mean, this is not just this. I mean, Minecraft, World of Warcraft, all of these games, you're doing advanced CAD. Well, Minecraft is not so advanced because it's blocky, but still, you're designing creatures. So why isn't CAD software in the same? Yeah, and to me, to really advance, it's going to have to get to that level. Yes? Yep. Yeah. So today, yes, ceramics are now fairly good, and you can make dental crowns and bridges in ceramics. We are short of metals. So you can do quite a few polymers, you can do quite a few metals, so titanium, cobalt, chrome, stainless steel, aluminium, precious metals. Various ceramics you can do, but it's still, we're short of materials. We need more plastics, we need more metals, we need more different types of ceramics. Plastics, yes. So you do have multi-material plastic machines today. There have been some universities working with multi-metals where they can do functionally graded metals where they'll shift from, say, steel and then gradually turn into copper in the same part. But it's still early days. There's no commercial systems that'll do multi-metal materials. And of course, nothing today will do metal and plastic, which is the holy grail, would be to do metal and plastic in the same machine. Whether that ever happens, we don't, the melting temperatures between metals and plastics are just so radically different. But yeah, I mean, so to answer the question, yeah, multiple plastic materials, yes. Multiple metals, no, not yet, but we're close. And then real multiple materials. So electronics is another big area. A company called Voxelate and a few others just got big funding in the US to develop 3D printed electronics. Because you think about most products, it's not just plastic or metal. It's plastic, metal, electronics, software, all combined. So ultimately, we do need a real diverse printer that can do all of the above, but we're not there yet. Spore Creature Creator, and it's a free download. I think you can pay to buy extra heads and extra things, and then you can sell your creatures to other. And you can, in fact, 3D print your creature directly from the game. And then you get a color creature in that FedEx box a few days or weeks later. Yep.
Yeah, I'd just like to add on a previous question that there's a huge online database called Inventors,
Yeah.
where there's millions and millions of miniature designed objects, everything from mugs to iPhone
Yeah.
cases, and it's totally free. You just download
There's Thingiverse, there's GrabCAD, there's all these growing community. And again, it comes back to that open source stuff I was talking about earlier. More and more of this stuff is becoming open source. So often you don't need to design yourself. We'll go here and then. Yeah. So today, plastic or metal, it's still what I would consider high value products. So it's still expensive. And that tapware at $12,000 is a good example. For luxury goods, absolutely. For high value products, so medical products is a good example. Medical products are always high value. You tend to sell a medical, like a hearing aid, you'll sell for several $1,000s. So whether the shell costs you $2 injection molded or 20 cents injection molded or $20 makes no difference in an inexpensive product. So it's value of the product. So today, stainless steel powder, for example, costs you about €70 per kilo. Stainless steel sheet metal costs you $6 or $7 a kilo. And the same with plastics is even more than that. The difference between 3D printing material prices. So in my opinion, the manufacturers of materials and machines are still thinking rapid prototyping. And with prototyping, you don't care how much the material costs. But manufacturing, absolutely you do. But interesting, a lot of the patents have expired on a lot of these technologies. So now we're starting to see new technology, or lower cost technology, and I think we'll also see lower cost material. So at Euromold, which is one of the big shows this week, they're announcing the first low cost laser sintering system, the powder-based system, for under €10,000, compared to the cheapest one is €200,000 currently. So you can see how that's going to change the equation of things. Yep. It never pays to wait. Buy one now. Seriously, I mean, next year there will be a newer, better model, and it'll be cheaper. But buy one now, because now it's not about the printer; it's about the creativity it unleashes. And now, as I said, $500, less than $500, you can buy a kit set that you build yourself, a fully assembled one you can get for under, call it between $800 to $1,500, and the slightly more expensive ones like the MakerBots might be around $2,000. I guarantee you within the next 2 or 3 years, we will get a 3D printer that's around the $200 range, that will be safe to use, easy to use, and that's going to be the best-selling Christmas present that year. But it's not a lot of money. As a designer, as an engineer, as an artist, as a hobbyist, to spend $500,000 or $800,000 on a tool that really allows you to try your ideas out, it's a bargain. So you can't afford not to. But again, just to repeat what I said earlier, these 3D printers are fantastic, but they're not the same as the industrial machines that you would get. So you need one of those to test the idea. Then once you want to print your part for real, there are plenty of online bureaus, like Shapeways, for example, where you can upload your file, get it printed out of stronger material. So I mean, to give you an example, this is on a laser sintering system. This is real engineering plastic that you don't need to worry about breaking. If you did this on one of these desktop 3D printers, chances are it will just split open if you did that. But yeah, buy a printer now. I mean, as I said, they sell them at MediaMarkt. Yep. All right, as it happens, in June we got one of these machines, a laser sintering machine. We have been doing a lot of work for the biomedical engineers already with this. So yeah, come and see us. This is now our main machine. We've got a bunch of other machines, but now that we've got this one, all the other machines have become research machines. So we're doing materials research on a few of them. We're doing research on printed electronics on a few of the others. But this machine is available to all of university, and in fact all of Lund really, to come and use, to come and play with, to come and experiment with. And it's a great machine. We're working, hopefully this year or next year, we'll try to get a metal machine. And again, the idea is to have an open access lab for university people, company people, to come and play and explore and learn about the technology. Because it is, I would not recommend any company go out and buy one of these machines without first playing with it to see how it can really add value to the business. We do. Yeah, so we do have a syringe-based printer that'll print anything you can put in a syringe, so including cells, for example. But the guys up at SP in Stockholm have got an EnvisionTech, which is a much more expensive version of the same thing, and we've got links with them, so yes, we could do that as well. But experimental work, I would recommend we do here with our little machine, and then once it needs to be taken to the next level, then we go speak to the people who have the more advanced machines and collaborate with them. Yes.
Housing like that.
Yep.
But the finish, how do you get that professional finish with color polishing?
There's again, it's one of the things we didn't have time to get into it today. The surface finish of these printers is relatively low quality. So there's always what you call post-processing. So after it comes out of the machine, you have to dye it to get it color. You can tumble it, which is you put it in a washing machine full of ceramic beads and roll it around for 3 hours, and that smooths it off nicely. You can sand it, you can paint it, but that takes labor. But having said that, the finish on that is not too bad. So depending what it is you're trying to do, you may be able to use it as is if it's not a visible part. But if you're trying to get an iPhone surface finish, that's going to be a lot of elbow grease to sand and polish. I mean, for example, we've got a printer that'll print in clear resin. So if you want to make a lens, you can use that. But typically, it'll take me somewhere between 3 to 6 hours to polish a lens to make it optically clear. And that's hand sanding and polishing, so it's a lot of extra labor for that. Today, they are getting better and better in quality, but it's still always going to be some post-processing needing, absolutely. Yes?
I have two questions. The UAV method that you have designed, does it have the same lifetime as a conventional design? And do you have components that are designed for airframes with higher speed than UAV?
Oh yes, yeah, absolutely. So yes, well the short answer is we don't know because we did this about 3 years ago, but in principle, it'll have exactly the same lifespan as the manually made one. The materials, so the titanium, the 3D printed titanium, is as good as cast titanium. If you heat treat it afterwards or HIP it afterwards, you'll get up to forge strength. So you'll get up to a good, strong part afterwards. So the lifetime will be the same. And there are now over 300,000 flying components, 3D printed components. So the Boeing Dreamliner has a whole bunch of 3D printed components. The F-16 fighter jet has a whole bunch of 3D printed components. The Airbus 380. So these are commercial airplanes flying 3D printed brackets and so on. Today, I would say not vital parts yet, because part qualification to guarantee that they're going to withstand the forces, it's all being worked on. So currently, it's all brackets, ducting, non-vital parts that if it fails, it's not going to be a tragedy. But none of those parts so far have failed. So.
Do you have experience of junction of the metal parts and plastic parts?
Typically, the bigger problem is junction of metal parts to different metal parts, where you start getting nasty things happening. But metal to plastic typically is less of a problem. And they do that all the time, where they'll make seals out of soft nylon, for example, and so on.
Thank you so much for an interesting. I just have one question for you. When we looked at the picture of the supply chain, you had today and then tomorrow with a much shorter. What time span do you expect?
It's already, we're already starting to see, so companies like Federal Express, DHL, are now looking at this sort of service where instead of shipping a part from, say, San Francisco to New York, you essentially upload to the cloud, download at the other end, and print it on demand at the other end. Mm-hmm. But already companies like Shapeways, like Materialize, like Cubify, like Sculptio are these sort of service bureaus that provide it as a service, and they will print often in the country. They'll have bureaus in the country, not always, that you want to print in. The pricing still needs to change quite a bit, but it is starting to happen now. Within the next 10 years, I think we'll see a boom of this in countries like Sweden, where we'll start to see spare parts being manufactured locally instead of sending them out to China, say, for example. So yeah, the next 5 to 10 years.
Yeah, perfect. I'm very glad. I'm still waiting for a combustion for my car that broke, so hopefully that will fix itself. Thank you so much for a very interesting morning.